Let's talk about biochemistry. In this review, we're going to talk about the different things that make up these very foods, from the proteins and the fats that are in the corned beef cabbage to the carbohydrates, not only in the starches, but also in these greens, the cabbage here, but also the fact that this delicious corned beef, I don't know if your family's like mine and you're going to be enjoying that, but this delicious corned beef holds moisture a great deal more than it would normally because it is so salty, and why that is. So let's get into it and let's talk about biochemistry. The first thing that I want to review is the 4 different groups and how you know whether a molecule is within each group depending on the elemental makeup. So remember, carbohydrates, I'm going to show you the structures in a little bit, but carbohydrates have carbon, hydrogen, and a lot of oxygen relative to the other elements. So that is why one way to know, because lipids also have carbon, hydrogen, and oxygen, but they don't have very much oxygen relative to the other 2 elements. No, all of them have carbon and hydrogen. You cannot be an organic macromolecule if you don't have carbon and hydrogen. All of them have it, but the way to know is to look at how much oxygen, if they only have carbon and hydrogen. That's one way. Phospholipids, I'm going to show you the structure and remind you of that too. They also have that the phosphate in it that gives it the phospho name and makes it, the hydrophilic head. But that's a good indicator. Also, proteins, and we're going to get into the structure a lot with proteins because they like asking about it. It has carbon, hydrogen, oxygen, and nitrogen, and sulfur in some R groups, some of those cysteine R groups. To remember, I remember HONC, H-O-N-C, or HONCs. That's a weird mnemonic, but it works for me to remember the elemental makeup of proteins. And then nucleic acids, which we're going to hit a whole lot more later in the year, especially as we get into how to make them. But they have COHN and phosphorus. Every nucleic acid has phosphorus. So this is the elemental makeup. Now let's talk about the structure. So oftentimes people mess up, if they're going to mess up something, they're going to mess up carbohydrates and lipids, specifically because some lipids have rings. Carbohydrates are always going to be isolated rings in some way, and there's going to be an oxygen linking them. Whereas in lipids, specifically steroids like cholesterol or testosterone or estrogen, they're going to have rings too, but they are tightly linked together, and there is almost no oxygen in them at all. You see this little oxygen here. You see a couple of little oxygens here. If they're in the fatty acid chain form of a lipid, you could see, again, remember, they're all carbons and hydrogens where these lines come together, but very, very little oxygen, whereas every single carbohydrate monomer called a monosaccharide is going to have oxygen in it. So you get oxygen, a whole bunch of oxygen, a 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. Lots of oxygen means it's a carbohydrate. But carbohydrates don't just stay in this disaccharide form like this. I believe this is fructose off the top of my head. Anyway, it's a disaccharide because it's got 2 monosaccharides together. But if you join a whole bunch of them, either they're going to form a nice chain like this, which stacks really nicely like this, which is how you get cellulose, how you get cell walls, how you get that delicious cabbage that is harder for your body to digest than starches. Starches are oftentimes chained. You don't really need to know the difference between alpha and beta glucose, but knowing that these stack really nicely, even amylose is not going to be stacking as nicely as cellulose. When they get more branchy, they're easier to break off, and we have enzymes that can break down starches, like in potatoes and carrots, and glycogen, which is how we store our excess glucose in our liver, in our muscles, things like that. So this is carbohydrates, especially when you get to the polysaccharide level, where you have lots and lots of these little guys like this that really look like this, all linked together. And then lipids, again, we've got the steroids, we've got fatty acids. This is unsaturated, whereas this one would be saturated because it doesn't have any bends in it. Triglyceride, that is typically how most fats are going to be stored with the fatty acid tails. But phospholipids, this is what your membrane is going to be made out of. Remember, there's this part up here that is the charge part, the hydrophilic head, whereas the hydrophobic tail, these down here, are going to be the hydrophobic part. Remember, the more carbon and hydrogen you have in you, the more hydrophobic you are going to be. Whereas the more oxygen, the more nitrogen, the more phosphorus you have, the more hydrophilic you're going to be. Now let's talk about proteins. Proteins specifically made up of amino acids. Remember that there is going to be an amino group or an amine group, a carboxyl group or a carboxylic acid group, the carbon in the middle, and then the side chain that's going to change. There is 4 levels of structure. All proteins have an amino acid linked chain. So all of them have a primary structure, which you can think of as like the alphabets, the letters. Whereas secondary structure, now almost all proteins have a secondary structure. You get long, and eventually the carboxyl groups like to combine with the amine groups on different amino acids, and you get alpha helices and beta pleated sheets. Remember, there's hydrogen bonds holding these together, so they're really, really weak if you have secondary structures. And then tertiary structure, that is where the alpha helices and the pleated sheets are going to come together. If secondary structure is the words where the letters are coming together, tertiary structures, you can think of like sentences. It's the 3D structure, and all proteins are definitely going to have a tertiary structure. All will have a primary, all will have a tertiary. Almost all of them have a secondary structure. It's only the really big proteins that have more than one polypeptide chain that is going to be a quaternary structure, where you have, you can see this polypeptide chain here combining together with this one here. We're going to talk about these actually in the current unit, but if you have 2 of them together, they're called a dimer. And again, to finish out the analogy, if you put sentences together, you have a paragraph. Now, all proteins have that sentence form, but if you put more than one together, then you get a quaternary structure. And then this is just to remember what's holding them all together. So primary structure, that is a peptide bond. It's a strong covalent bond formed by dehydration synthesis, actually at the ribosome. We'll talk more about that later. Hydrogen bonds, these are the weakest bonds, and these are the ones where the amino group and the carboxyl group of amino acids are going to come together and link these together to make the alpha helices and the beta pleated sheets. And then the R groups are going to create ionic bonds, hydrogen bonds, disulfide bridges when you have 2 sulfurs together, and then hydrophobic interactions when you have lots of carbons and hydrogens alone. Yeah, it's going to be part of the protein. It's going to lead to 3D folding because of those R group interactions. And then quaternary is the same rules as tertiary. It's just if you have different multiple polypeptide chains that you're going to have those interactions. I'm going to stop now and ask for any questions. Are there any questions? I've got more to talk about, but I've already been talking at you for a little while, and I want to check in before I keep going? You could say them aloud or drop them in the chat, or I can just keep.
Which structure is the weakest again?
The secondary structure is the weakest because, great question. It is the weakest because, let me see. No, I can't do it. It's the weakest because hydrogen bonds are really, really weak. They're not actual, sharing of electrons or anything. They're just like due to a slight imbalance between things that typically have oxygens and nitrogens, where there's that imbalance of electrons. But great question. Secondary is definitely the weakest and easiest to break. Hydrogen bonds in tertiary are easy to break too, but you have ionic bonds and disulfide bridges that are much stronger, that hold tertiary better together than secondary. Okay, and then I have a chat question as well. Great question. It is the I'll go back. The unsaturated fats that have the bends like this, where this is going to add a kink into the saturated fatty acid, or into the fatty acid, I should say. The ones that have no double bonds and no excess bends at all are going to be the saturated ones because they have every hydrogen that they can possibly have. Whereas this, because it has a double bond, is not going to have as many hydrogens as it can have. So it's not saturated with hydrogens. Great questions. You're very welcome. All right, so dehydration synthesis, I mentioned before, that's when you're building things up. So, in fact, I'm going to think of it this way. Hydrolysis is when you break something down. When I am going to eat that corned beef cabbage later today, I'm going to take in the proteins into my body, take in that delicious meat, and the enzymes in my body are going to break it down into its individual amino acid parts. That is hydrolysis, where water is going to come in and separate the monomers into different parts. These are monosaccharide monomers, but it's the same general process where water comes in and breaks things down. But say I've worked out and I've gotten all sorts of jacked, and now I'm going to start building muscles. Well, those amino acids that my body has absorbed and put in the bloodstream are then going to be recruited to the site of muscle injury, where they are going to then make new muscle proteins. That making of new muscle proteins is going to be dehydration synthesis, where you are pulling out this water and building these the new molecules together. Again, I'm using amino acids in my verbal analogy, but it works the same way with monosaccharides as well. Okay. And then let's talk about lipids. So lipids are one thing that they don't really build, large structures out of each monomer. Most of the time, lipids are just going to exist. They're going to pack close, but they're not going to be linked to one another. But the reason that they pack and they make this phospholipid bilayer, remember, is this is a watery environment around a cell, and this is a watery environment inside a cell. They're both watery environments. But what separates them is this cell membrane made of a hydrophilic head that likes the water. But those hydrophobic tails, they are going to be inside of the actual membrane itself. They like each other. They like hydrophobic likes hydrophobic, so they're going to stay inside. You can also see just in this cartoon that this is probably a saturated fatty acid. It is very long and straight, whereas this one probably has a double bond right here that you can't quite see that leads to the kink, and it is an unsaturated fatty acid. And then remember, this is the hydrophobic head. It's got the nitrogen that's charged and the phosphate that's also charged. So that makes it like water. And then just a quick reminder of, and this came from our POGIL that we did, what things can get through a membrane. Ions, even if they're small, negative, positive, they cannot get through this hydrophobic region here. So they are going to be kept to one side of the membrane. This is a polar molecule. Glucose is polar. It's got a lot of oxygen in it. So it can get through a little bit, but still it's pretty large and it's polar, so it cannot get through. Small things, so this is a little smaller, and urea has nitrogen in it. So it can get through just a little bit better. But the only thing that can get through really easily and is going to have no problem getting through the cell membrane is going to be small hydrophobic molecules like carbon dioxide. Carbon dioxide, even though it's got carbon and oxygen, the carbons balance out, and it's a real small molecule, so it is hydrophobic. Oxygen gas by itself can also go through a membrane really easily. This is why our lungs work as well as they do. The oxygen can get easily in and easily out at that lung cell barrier there. Let's see here. I'm going to talk about a new topic after this. So I'm going to again check in and see if there's any questions about the last couple of slides. Then we're going to talk about osmosis.
For dehydration synthesis and hydrolysis, is it for all the macromolecules?
Yeah. This is really what's going to link all macromolecules. Even like I said, the lipids, they don't make very, very large macromolecules like carbohydrates will, and nucleic acids will, and proteins will. But they still, if you're linking a fatty acid to a glycerol to make a triglyceride, like I showed a few slides back, it's still going to be this sort of link or breakdown that happens. Absolutely. It's just very, very frequently water comes in and breaks things down in our systems. Great question. Any others? Okay, then let's talk about osmosis and water movement. So cells generally are going to be permeable, meaning they let water into and out of them pretty darn easily. They have little proteins called aquaporins that make that possible. And because of that, it leads to tonicity. So if you put a cell in an environment, it is going to react to that environment by putting water in, pushing water out, taking water in, or staying basically neutral with no net movement of water. So if you put a cell in a hypertonic environment where there is a high amount of solute, and oftentimes when I think of solute, I just think of like salt. I think it's a good analogy, and it's oftentimes even in our bodies, the saltier the environment, the more hypertonic it's going to be. That means there would be more solute outside, so saltier outside, higher amounts of water inside. So because of that, the water wants to balance things out. And so the water would move out. That would lead to a shrinking of the cell. This happens in both plant and animal cells. The cells shrink to go to where there's not as much water. In an isotonic environment, like saline, like you would get, it's awful. Like a saline you would get if there was, you get any sort of injection, or if you use eye contact solution, that's going to be isotonic, where you're going to have equal amounts of solute inside the cell and outside the cell, equal amounts of water. So there will be water moving both ways, but you won't see any change to the cell. The cell's just normal. Whereas hypotonic, I like thinking of hypo like hippo. Hippos are big and fat, and that's essentially what happens to the cell. If there is more solute inside the cell relative to the outside of the environment, then there is higher water inside, so the water wants to go into the cell, so the cell will swell up like a hippo. Remember, this is a very, very dangerous scenario. It's why you shouldn't drink, pure deionized water. It's oftentimes much better to drink something with a small amount of ions in it. I ruin cells in my studies because of hypotonic environment in that cell or outside the cell. It will cause cells to burst. Keep that in mind. And then I'll remind you about water potential, and then we're going to do a little sample problem. And I know some of you, this might be all you get to because you've got the government review after this, but if you can stay on, we are going to go through the problem next, and then also the an FRQ, where I'm going to give you time to do it, and then I'm going to go through what the correct answers. And again, I will record everything so that you are good to go. I hope I've been recording everything. Yep, I'm still recording everything. Good. Okay, so water potential is really a way to measure, to remind you where water is going to go if it's not super obvious which one is going to be more concentrated. So you can use these two equations here, where the overall water potential is the pressure potential plus the solute potential. And this is actually what is shows up on your equation sheet, which is why I have it right here to remind you of it. The water potential will be equal to the solute potential of a solution in an open container. Could look like this because the pressure potential of the solution in an open container is 0. They give you a whole paragraph right here. But just to remind you, this becomes 0 if it's an open container, so that your whole overall water potential is just going to equal your solute potential. And your solute potential follows this equation right here, where it's negative ICRT. Where I is the ionization constant. It is 1 for sucrose because sucrose does not ionize in water. But if something does ionize in water, like sodium chloride, for instance, then you would need to list the number of ions. Sodium chloride is the most frequently used one, and it breaks down into sodium and chloride. So your I would be 2 in that scenario. C is the concentration of whatever the solute is. Again, it's going to be given usually in units that have a big M for molarity. R is a pressure constant that is 0.0831 liter bars per mole Kelvin. Take note of this Kelvin because that is the temperature, what you must convert the temperature into. So the temperature in Kelvin is always just the degrees Celsius plus 273. So I want to do a practice problem here. It's got these two things here. So I'm going to give you maybe a minute in order to solve this, and then I'm going to go through how to do it. And the constant again is 0.0831 if you don't have it down anywhere. Got a little bit of time remaining. Okay, got a chat here. The ionization constant. So I probably will go through the problem now, just because I want to make sure people have time. The ionization constant comes from NaCl. It breaks down into 2 ions. So because of that, your I would be 2. So let me pull up my hover cam here. And I'll go through this. And again, if you need to leave, feel free to. I'm going to go through this solution. The correct answers was side 1 was negative 44.5 bars, and side 2 is 9.9 bars. And it's always going to go to the one that's more negative. So there we are. Okay. So with the 2 sides, we had the beaker like this. And this was side 1 and this was side 2. And it said side 1, was 0.9 molar and side 2 is 0.9 molar. And that's really the only difference between the 2 of them. Note, I use this overall equation to figure out the water potential. I set this equal to 0 because it's an open beaker. And then I can use this equation to figure out the solute potential to get the overall water potential, which is negative I CRT. So that I was 2 because NaCl breaks down into Na plus and Cl minus. The C is the concentration. So on side 1, it was 0.9 molar. In side 2, it was 0.2 molar. And then R was 0.0831, 0.0831. And then to figure out the temperature, you needed to convert to Kelvin. So it was 25 plus 273 and 25 plus 273. So side 1, I get a potential of negative 44.5 bars. Inside 2 was negative 9.9 bars. So because of that, the net movement of water would be from side 2 to side 1. Great question. Yeah, it's going to go from side 2 to side 1 because this is more negative. Whichever one more negative means more water needs to go there. Okay. All right. So we've got some people who have to go. You're very welcome. And that is totally fine. And that is how long I said it was going to go. So if you need to go, that is totally fine. At this point, I'm going to give you 10 minutes to work through that problem. And then I am going to go through that problem.